Okay, wow. Everything worked. So whatever karma I have earned apparently is getting spent today. There isn't a warm-up problem for today because we're starting a whole new topic, but there is a poll everywhere question that you should answer, and then let's look at the results at the end of lecture. Yeah? We'll see. Cool. Okay. All right. Come on in. Happy Wednesday, everybody. Let's see. Our usual reminders. Exercise 2 is due this Friday. Exercise 3 will go out on Friday. FYI, exercise 3 is going to be an example problem format of what the simulated midterm will be. So this is like I sort of told y'all, I'm experimenting with these new types of formats. So thank you for going on this journey together. But I figured it would be best if we sort of practice what I think the midterm should be like on an exercise. So that will be coming out Friday. I also wanted to just take this moment to give you sort of like a heads up as to what the calendar is looking like. So midterm goes out on Friday. That will be like some design work. And you'll have until Monday to submit your responses. Reminder that the midterm is individual. After you submit your design work on Monday, then, why would you do that, computer? Then we are going to release our designs, which is essentially, you could kind of think of that as like solutions. And then you will have until Wednesday to do your design review. So what that means is I'm going to give you some scenarios. I'm going to ask you to come up with a design for how to code a solution for those scenarios. So you're going to be asked to pick an ADT, asked to pick a data structure, and then I'm going to ask you to talk through how you would use those things to accomplish the prompt. I'm going to ask you to think about the best case scenario of your design, the worst case scenario of design, and then do your asymptotic analysis of your own design. There's a method to the madness. This is literally what an interview question would be if it was done properly. And also like really what we sort of do in industry. So that's why I'm trying to give you this type of opportunity. But we know that design doesn't happen in a timed like written paper kind of exam. So that's why you're going to have from Friday to Monday to write up your design. I will tell you that we are currently planning to make the exam the length of what we think would be an hour if you were here sitting in person, because it's a midterm and a midterm should be an hour. I know you might take longer because you want to look stuff up online and think about it, and there's going to be like some written aspects of it, but I am not intending it to be a very elongated assignment. I'm just trying to give you as much time to think and synthesize your way through it as you would like, so there's not that time pressure. And then between Monday and Wednesday, what I'm going to ask you to do is reflect on the design and then maybe look at our suggested design and then write a review of that design. And the method to that madness is that I've been obsessed with this idea of how to turn code reviews into an actual assignment in academia. Because in industry, code reviews is what we call like our university. Like the way that you learn the most about being a coder is a code review. So I can't wait to tell people that maybe I've cracked this and that we're doing code reviews as assessments. And so then your final grade will be the combination of the work you did in your initial design and your reflection piece. So for example, let's say that initial design, you just like really understood the prompt, you came up with some great ideas, everything's working the way that it's supposed to work. Your review will be, yeah, I agree with what I put together. Maybe here's some extra examples that shows that my design is really effective. Or if that first design through, you just didn't understand what we were asking, or you kind of went in a different direction, or you had some kind of funky ideas, then your review can be essentially, I would change everything about this design. Those 2 students get the same full credit grade. I don't care if you get it right on the first time. I care that you get it right in the combination of those 2 pieces together. Caveat, I know some people are like, well, then maybe I'll just like put some nonsense in the first one and then I'll just totally correct it after I see the solutions in the second one, as if we haven't thought of doing that ourselves. So you do have to put in what we're going to call a good faith effort on that first one. And we will be reading these. You can kind of like emotionally prepare yourself that this type of questions, they're going to be like short answers. So we're going to be asking you to sort of describe your design in sentence format. So just sort of, prepare yourselves. I almost in my head, and I know this is unfair if you're actually an English major, but like in my head, I'm like, this is the closest I'm ever going to get to an essay style exam. Next lecture, which is Friday, I will release the set of topics that you want to be familiar with before going into the exam. So we can talk about it a little bit more on Friday. But also, just FYI, there will be no office hours during the midterm. So from the Friday to the Wednesday, you're on your own. We will answer clarifying questions on the ed board, but it will probably be me, and I will be that like annoying teachery thing where I'm like, I'm really only clarifying typos or things that are really confusing, but I'm not trying to give anything away. So the point of this exercise is to see how much you individually have ingested some of the ideas of how we approach design for a software situation. Does anyone have any questions about the midterm at this moment? Yeah.
Is there going to be class on Friday for the 29th?
Oh, yes, there is going to be class on Friday the 29th. I think I picked a topic for that day that is obviously not going to be on the actual assessment, but one that I think is important, and I've always been trying to find space in this class to do. Pretty sure it's tries. Yeah.
So is everything like on the exam going to be like up to the Wednesday?
Yes, thank you. So everything on the exam will be up and through the topic of probably that we'll finish talking about on Wednesday. The topic that will be the end of the list of things for the exam is what we're going to introduce technically on Friday. And then we're just going to dive deeper into that topic for Monday and Wednesday. Yes. Any other questions? Cool. Like I said, this is an experiment, so I will also put out a sort of like feedback form during the exam because I want to hear how this goes for everybody. Maybe we'll move forward with it. Cool. Does anybody have any other administrative questions? Cool. Okay. New things. Okay, so we talked all about hashing for the last bit. And we were almost always talking about hashing as a data structure implementation of the map ADT. And that makes a lot of sense in the hash context, right? Because you have this kind of lookup value, and then you find what you're kind of searching for that fits very well in hashing. We're now going to move into picking up another set of data structures. And remember that technically you can implement any ADT with any data structure, but sometimes they don't fit as well as other situations, right? As you can imagine, a tree for a queue might be a little tough, right? But we're going to be delving into what I call branching data structures now. So welcome to our series all about trees. This is hopefully mostly a review from 143 for you, but remember that there's this idea of something called a tree. A tree is a collection of nodes, so it is a cousin of the linked list, right? Where if the linked list is a front pointer to a node, and that node is technically an object, and that object has 2 fields, a data field and then a next field, right? And it's just this sort of chain of these little objects. That's exactly what a tree is, except this node object, instead, it's got 3 fields. It's got a data field, and it's got a left field and a right field. It functions exactly the same way as linked lists. We just have 2 possible directions we can go off of each node. So this has all of the same situations of the linked list in that maybe it's a little bit easier to sort of like move things around. We only ever have the same number of nodes as we have pieces of data entry, but it doesn't benefit from that like all the memories in the same place kind of thing that arrays get. So we could have these nodes sort of scattered about. Here is that definition of node in code form. And just to sort of dust off some cobwebs, we call the top of the tree, we call this the root node, and usually we call this overall root up here. And so that's what the equivalent of front pointer is for the binary tree situation. If you can't tell, the BI in binary stands for 2 children. We're going to be talking about 2 children trees for a minute, but keep in mind that there can technically be any amount of references off of this. So you can have trinary trees, you can have n-ary trees, and so on and so forth. But often those things get quite unwieldy, and you'll notice that for the most part, we kind of stick in this binary tree situation. I know we also call them trees, and nobody ever said this to me in 143, but like, they're technically upside down, right? We call this the root and we call these the leaves. So if you're actually imagining a tree, right, we sort of have like, there's our tree. Yeah? Trees are inherently recursive structures because each tree contains a subset of trees. So this is the overall root, and it has 2 subtrees off of it, for which this is the root of this subtree, and this is the root of this subtree, and even those have trees inside of them, and this is the root of this subtree, and this is the root of this like kind of boring subtree. And so you'll often find that the code to traverse, to make, or to change a tree is itself recursive, which is why we spent all that time talking about the runtime and how to analyze the runtime of recursive code. Hopefully all of that is mostly review. The one thing that I don't really remember them talking about in 143 is this concept of height. We are now going to become obsessed with the idea of the height of the tree. And the height is the number of edges contained in the longest path from the overall root to some leaf node. So, in this case, we can see that there's 1, 2, 3 edges in the longest path. There's technically 2 longest paths here. So this tree has a height of 3. Any questions about the basic terminology there? Yes. Yes, essentially it is about how many levels there are. And I'm going to go into a bunch of delightful mathy details about why we become so obsessed with height. Yes?
In CS 143, there are a few questions that had the root start at level 1. Are we completely ignoring that as like height? Or like...
Yeah, so when I say height, I mean sort of like this distance from top to bottom. We used to be concerned about like labeling levels as numbers if we were doing that tree method problem. But from here on out, since we're not doing that, we don't really care too much about like, oh, we call this level 1 versus level 0 kind of thing. Yes?
Is there any sort of tree where like 2 nodes would point to the same?
Ooh, the question is, what if we had 2 nodes that pointed to, like, say, for example, this 6 also pointed to this 4? What this becomes, if I add this singular reference pointer, is I no longer have this idea of like roots to leaves, but now I have this almost kind of like cycle situation in here. And what I have just done is I have taken this from the superset that is tree into the subset of something we will call a graph. And we are going to spend 3 weeks of this class talking about those magical things. They're also like my favorite. So I'm really looking forward to it. But just that change. So for right now, trees do not have that type of thing because trees must be directed in acyclic, which is just a fancy way of saying there can't be any of those cycle things going on. There's always got to be sort of like a path from the root to some leaf, and you know, like singular directional. So if they're both pointing down, and this is also an interesting piece, right? Because right now, these do have little arrows on them. So like theoretically, I can't follow back up, right? Because 4 doesn't have any contextual reference of who its parent is. So you're right in that technically it's not a cycle, but this would be like a closed loop. And that's not something that fits our definition of tree. So in this case, no, we do not have 2 parents to any singular node. Every node must have at most 1 parent. Yeah, that's a cleaner way to say that. Good questions. Oh yeah, in the back. What's an edge? Oh, great question. I used that word because that's what we call them in graphs, and I didn't even notice it. Thank you. An edge is literally just a pointer. An edge is a connection between 2 nodes. In trees, we call them pointers. We call them references. I might call them edges by accident again at some point, but I'm just referring to this idea that I know how to get from 1 to 3. And just for context, we're going to draw them as arrows, but never forget, this is just a memory address. And that memory address is actually just like a hex value, so it's actually just a number. Yeah.
Like just so it's easier for me to remember. Like, is it okay if I remember it as, oh, the root has a height of 0? And I just count down the nodes from here?
Yeah, I think that's reasonable. So if we want to do that, then like maybe this is 0, 1, 2, 3, and that gives us our height. Yeah, that's reasonable. Let's talk about why that makes sense. Oh, here's some practice with the height. That's reasonable. Okay, so here, let's call this tree A. What do we think the height of tree A is? 2. Yeah, I agree. Let's see animations. Yeah, cool. 2, because here's 1 level, here's 2 levels. Or if we wanted to do it in that way that we were just suggested, maybe this is level 0, maybe this is level 1, maybe this is level 2. Okay? Now, how about tree B? Does anybody want to guess at what the height of tree B is? Yeah. 0. I absolutely agree. So a tree, quote tree, that's just 1 node is a valid tree. You could kind of think of it as like a stump. And a stump doesn't really have height to it, right? So this is a height 0. We also make this choice because this makes some of our math work. So then if we have instead tree C over here that doesn't even have that first node, anyone want to take just a wild guess as to what we think the height might be there? Ooh, null's a good guess. Was that going to be your guess too? No height. Good. Yep. Essentially. Yeah. So again, this is a to make our math work situation. Sometimes we will say this has a height of -1. We don't actually mean this is like an underground tree. It's just if we have a negative number, then that's a way for us to write our math to recognize like, oh, that means no height. So yeah, you can think of a tree with null. Overall root pointing to null is no height, NA, or sometimes mathematically it will be represented as -1. Here is the math that I told you that would be helpful because of these things. So for a binary tree of height h, the maximum number of leaves, meaning how many things are in this bottom level, is always going to be 2 to the h. The 2 comes from how many children each node has, and the h comes from the levels that have generated that number of parents. So then the maximum number of nodes is technically 2 to the h plus 1 minus 1 overall, because then that sort of includes our overall root. So that's a way for you to calculate the maximum number of leaves and the maximum number of nodes. Now, this context of max, that's a situation where the only null children must be down on this level, where every child field that isn't a leaf must be non-null. That is a maximum situation, and so we would call this tree full. So if this is a full tree, looking over at this odd cousin on the right-hand side of the screen, you can see then, technically for a binary tree, we sort of decide that like the minimum number of leaves is 1, because that situation would just literally be like overall root points to a single node. So that node there, then that's a leaf. And a leaf, by definition, is a node whose left and right child are both null. That's the definition of a leaf. If either of its children are not null, then it's what we would call a branch node. We're really committed to the tree analogy here. Computer scientists love it. We love the analogy. So then the minimum number of nodes in any tree is h plus 1. Because if h is the longest path, and paths must be created by some reference, then the minimum way to build a tall tree is to just only make like one child off of each thing. And so that's why we get that height plus 1. This here, gosh darn, if that doesn't look like a linked list, right? It's just like, it's kind of like a linked list askew instead of like a linked list forward, right? This is unfortunately not what we want our trees to look like, because what a waste, right? Like then we might as well have used a linked list. This is actually we call a degenerate, which feels very judgmental, frankly. But this is what we would call a degenerate tree, because as you can imagine here, what we've got is we've got a really tall tree for only 4 nodes. Right? Like we could instead have a tree that's full, and that would have a height of 2 instead of this height, which is 3. So that like fakey linked list situation is the degenerate tree. And keep in mind, remember in hashing how our worst case scenario in the chaining hash map was like n collisions, which ends up with just a empty hash map holding a linked list? Kind of similar, like the degenerate worst case scenario for trees often also ends up being like, whoops, we ended up with a linked list. Yeah, question. So the maximum number of nodes here is going to be 2 to the h plus 1, which is then recognizing that there are 2 nodes at each level. Like we're adding a whole nother sort of series of 2, right? So like if we had a height here of, let's say 1, and we had this node, and this node, that height would be 2 to the 1 plus 1 minus 1, which would be 2 squared plus minus 1, which would be 3. And so that minus 1 actually really comes from the fact that this overall root, it doesn't have a buddy, doesn't have a sibling. So that minus 1 is really just saying only child at the top. Yeah, great questions, y'all. Okay, so those are just binary trees. Meet an incredibly useful flavor of binary tree called the binary search tree, or BST. Interviews love questions about binary search trees. They're so fun and funky and easy to make up questions for. They come up a lot in interview questions, just FYI. So what a binary search tree is we've added something we're going to call an invariant. An invariant is like a rule that dictates whether or not this thing can be considered a binary search tree. Just like how if you have rectangles, for something to be considered a square, it has the invariant of equal sides. Similar situation here, where we're sort of like adding these kind of rules that will group something into what we call a binary search tree. And the invariant for a binary search tree is for every node with key k, so this means like with the data, the left tree can only contain keys smaller than k, and the right subtree can only contain keys greater than k. So what's magical about this little invariant here is now we have added a way to order the nodes in relation to one another, which means if you're looking for something, at each moment that you're traversing the tree, you kind of get this signpost moment, and you can decide going left or right. Do I have any more animations here? So, as you can see here, sorry, that's when I like lean on it with my elbow. 10 is the overall root. Everything in this subtree is less than 10. 8 is less than 10, 2 is less than 10, 9 is less than 10, 5 is less than 10. Everything in the right subtree is greater than 10. And this applies recursively. For 8, everything to the left of it is less than 8. 2 and 5 are less than 8. Everything to the right is greater than it, which is 9. So if we start to think about what this means then, if I was asking you to find the next number in our collection that is less than 10, but is as close to 10 as possible, does anybody have any intuition already as to where in the tree we would go? We're trying to find the number that's next closest but still smaller than the overall root. And we could do this by kind of traveling these, yeah.
The first black one.
Yeah, exactly. So it's sort of like, well, if we know we want it to be less than, then at our signpost here, we'll go left. But if we want it to be the largest of the things that are less than me, then I go all the way to the right. So it's like if I'm looking for the thing closest to me at the overall root, I go left once and then all the way down to the right. If I'm looking for the thing that's closest to me but is just greater than me, I go right once and then I go all the way down to the left. And that applies recursively throughout it. And so now I've got these sort of like signposts and I can find these deterministic ways to find like, oh, who's closest to me in value? Or, for example, where would I go if I wanted to find the largest number in this entire set? Yeah.
You would just keep going until you couldn't go right.
Yes, you just go right all the way down, right? Take all the rights you can. Yes, and then you had a question.
Yes. So how do binary search trees deal with duplicates?
How do binary search trees deal with duplicates? Conventionally, is this on my next slide? No, okay. Conventionally, we are going to be talking about these trees in terms of implementing the map ADT. And very conveniently, the map ADT says no duplicates. So you will often find in a lot of these conversations about binary search trees that they just say no duplicates allowed. Technically, you could add duplicates, but you would have to just decide, you know, which side or the other they're going to fall on. But a lot of times, duplicates will make all of this a lot more complicated. So for the most part, from here on out, consider all of our binary search trees to be unique values only. Great clarifying question. Okay, apparently this next slide is about the ordering recursively. Yep. Oh, yeah. Thanks, Past Casey. These are beautiful animations. But there, you can see that's what I'm trying to get at there. Aside, this is more what I was trying to get at there. Technically, remember, map is our ADT. Map just says, I need some way to associate a key and a value. I need to be able to put it and get it and then check if that key's already used. So for now, what we're doing is we are talking about implementing a map, but using a binary search tree. Now, what that means is that really the node then has to have space for both the key and the value. But all teachers everywhere collectively agreed it's such a pain in the arse to draw out both the key and the value fields that we just like don't draw these things. And then I realized after teaching this for a few quarters that people didn't realize that because I never said it to them, which is obviously my bad. So from here on out, just imagine that when I'm drawing these little nodes that seems to only have 3 things, really what I'm talking about is the key and that there's like technically a value field sort of like associated with each of these nodes. I'm just being lazy and not drawing it. Yep, you can read this. Okay, let's talk about how we then navigate these trees. So let's say I've got two maps. I've got, here's map A, and here's map B. Which one of these is a binary search tree? B. Great. Hopefully you looked at this and right away was like, whoa, 9 is not greater than 32. That breaks the invariant. So map A is just what we would call a binary tree. And map B is what we would call a binary search tree. And we've implemented these maps, and let's say we're trying to check if either of them contains the key of 2. If I was trying to contains key on map A, I have absolutely no idea where 2 may or may not be in the tree, which means I'm going to have to do what we call a tree traversal. So like in 143, do they still do the sailboat method? Yeah, okay, cool. Literally, this is what's happening. And technically what that means is I'm going to check 32. That's not it. I'm going to check 11. That's not it. 50. That's not it. 5. That's not it. 38. That's not it. And then I come back up and I go 9. That's not it. 8. That's not it. 10. That's not it. Finally, 2. But look, I had to check every single thing until I found it. It's essentially the equivalent of a linear search, right? Just start at the beginning and look at every single thing until you find what you're looking for. Because there's no rhyme or reason as to where something may be. Enter the magic of the binary search tree. I'm going to start here at 10. If I'm looking for 2, do I go left or right? Left. So I'm going to go here. And what that then means is I don't got to look at any of this. If this was a perfectly full tree, that means I've just eliminated half of the possibilities where I might need to look. Because I'm guaranteed that the value I'm looking for is nowhere in that right subtree. Now I'm at 8. Do I go left or right? Left. I do. And then like magic, I found it. But in that process too, I also eliminate again all of the possibilities from the subtree I don't take. So as you can see, here it took me 1, 2, 3, 4, 5, 6, 7, 8, 9 checks to find it. Here it took me 1, 2, 3 checks to find it. Yes.
So if it was implementing like a map, then those values would instead be hash codes?
So what this would probably be is you can think of these as like keys. And so if we take it back to like our physical dictionary example, maybe these are the words. And then there's secretly like a little value field that's the definition, like attached to each of these.
I see. Yeah, that makes sense.
Cool. Yeah, let's see. There in the back.
So I guess like a quick question about like how you're able to eliminate half of it. What if like one of the branches, like the left branch from 32, like that was the 2 instead of, because would that also be possible if the 11 instead of the 2 would be less than 32?
So what if, so you're asking what if the 2 was here instead? Yeah. So if that was the case, I would have broken my binary search invariant, and this would no longer be considered a binary search tree. So I can only justify this thing that I'm like, I don't even need to look over there. I've eliminated half the possibilities because I've been promised this is a binary search tree because the invariant must apply recursively. So it has to apply up here, but it also has to apply to 32. And so in that case, like, you know, we've theoretically broken it because 2 is greater than 10, and that can't be the case. Yes?
So kind of going back to what he was talking about with hash codes and stuff. So if we're thinking about like the worst case for binary search trees, technically speaking, we can have literally everything on one side, right? And then
Worst case, we could technically have everything on one side, right? Is there anything preventing that right now? Great. Continue your question. Yeah.
Right. So then now it's a question of like implementing hash codes, and then I'm assuming like compare two functions later on.
So yeah, so in order for something to be inserted into a binary search tree, it must have a compare to function. So it has to have some definition of less than, greater than.
So then is that where like all that comes in?
Yeah, so, okay, and part of the reason I got really excited about your question is because the thing we're going to start talking about on Friday is specifically this idea of, like, how do we avoid a degenerate binary search tree? Because isn't that inconvenient? And so what I will say is that you're absolutely right. You could have absolutely everything just like one long line. Again, stretching the way that we're thinking, what ordering of data would result in a degenerate binary search tree? What order of adding things into the tree would cause us to just have one long line of nodes? Yeah. Ascending or descending order. So if my set of data is already sorted and I just go, okay, add the number 1, maybe it becomes the overall root. Add the number 2, well, that's greater than. Add the number 3, well, that's greater than. Add the number 4, and we just end up. Same thing for descending. We'll talk about how there's trees that prevent that from happening, but yes.
So about runtime, like, would this still be linear, just O of like H instead of O of N?
Oh, what a great question. Yes. So I did do this kind of thing, and I'm glad you both stopped me on this because I was like, we could eliminate half of the possibilities. And then I was like, if it was full. Because if I have a degenerate tree, if I go to the right, in this case, there's nothing over here. So I'm not actually eliminating any possibilities whatsoever. So okay, fine. I was like, can I have some empty space to draw? Okay, so let's talk about for a hot second. So our best case scenario for a binary search tree is one in which every time we go left or right, we're eliminating the maximum number of possibilities. We're actually cutting the possibilities at that level perfectly in half. That is going to be then a full tree. So then, what's the opposite of that? What's our worst case scenario for a binary search tree? What would the tree look like in a worst case situation? I've been saying the word a bunch, and it feels very judgmental. Yes, degenerate. A degenerate tree, worst, is a degenerate. So, when you are writing code for tree traversals, every time you recurse, that's really the moment that you follow the signpost and go deeper down the tree rabbit hole, right? That's essentially the equivalent of an iteration in a loop, is every time we recurse, we go down another level. And so the taller a tree is, the more recursion we're going to have to do to get deeper and deeper into it. How many recursive calls am I going to have to make for a degenerate tree? Any ideas what that runtime might be? Yeah? Yeah, the number of nodes. Because, like, each node is its own level, right? So then we end up with an O of N runtime for a degenerate tree because it's just a linked list. So if our best case scenario is full and we're eliminating half of the things at each level, does anybody remember what the runtime is of an algorithm where we eliminate half the things? Yeah. Log n. Exactly. So our best case is O of log. So best case scenario, log n to get from top to bottom, which is our best case runtime of, finding the thing. Our worst case is n because that's if we accidentally have a degenerate tree. This slide is just asking you to practice and just showing what I essentially drew on the last page. But there you can see, right, without the BST invariant, we might have to search everything. With the BST invariant, we have to search those 3. But I think we covered that enough. Let's actually talk about some code. So here is the code for a contains tree or a contains key of just a binary tree. So you can see, here's our first base case, and that's really for our null case, like when we run off the end of the tree or if the tree has a height of -1. Here's our second base case, and that's if we've found the thing, then just return, get out of there. We don't need to keep looking through the tree. Otherwise, we have our recursive case where you can see it calls a recursive call either on the left or the right. This is kind of pseudocode. So this is, we're going to have to do both of them, right? So really we're going to need to do that, and then we're going to have to do the other one too. So if I was writing the recurrence of this, I might be base case, I don't know, that's some amount of constant time work, right? And then for our recursive case, we see that we've got 2 recursive calls. And one goes left and one goes right. So we know we're going to like eliminate at least me. So we're going to say like n minus like 1 kind of items there. But I don't really know that I'm going to eliminate anything. I can't particularly tell based on the fullness, right? If I look over at my binary search tree code, I have the same exact base cases. But then in my recursive case, I'm only making a singular recursive call. I don't have to recurse down both pathways because I know which way I gotta go. So instead, I now just have a 1 there. T of n. Sorry. And so I've already like dramatically improved my runtime in theory because I am only making a singular recursive call because I don't have to check the whole tree. So, continuing our conversation, which was delightfully just a little bit further ahead than my slides were following along, the other way to maybe think about this, so we were talking about like the best case scenario. So right now, this layout of tree, I would call this a full tree. The only null values are down on the leaf level, right? So each left and right is going to properly, is this the animation? There we go. Is going to properly eliminate half of the possibilities. So here's that recurrence that I was writing where we're going to assume the best case scenario of fullness. So we're going to cut n in half each time. We only have technically a coefficient of 1 in front of this recursive call. And then there's like, I don't know, some amount of non-recursive work. Maybe that's like this comparator right here. And then we've got some amount of base case work, which is like maybe, you know, whatever, those things there kind of situation. But another way to also think about these sort of like best and worst case situations is also like where the item you're looking for ends up being within the tree. So this tree is full, which is great, but we're going to end up with a very different like actual runtime if we like the thing we're looking for happens to be right here versus if the thing we're looking for is not in the list. Because if I'm looking for something that's not in the list, that means I'm going to have to explore as much as possible to process of elimination, determine it's not there. But because of the binary search tree invariant, that doesn't mean I have to look at every node to determine it's not there. I just have to follow down the path to where it's supposed to be. And if it's not in the spot that it's supposed to be, then I can sort of bail out. So as long as the tree is full, my worst case scenario still stays log n, but my best case scenario then ends up being that sort of like constant, it was the overall route, super lucky for me. So I need to think about not only what the structure of my tree looks like, that's going to impact the runtime, but also the value that I'm looking for, like where does it happen to be in the tree? And so for example, we know the thing at the overall route. Can anybody tell me the mathematical term for what that value would be if we're thinking about like statistical analysis of that set? Let's see. Where is the very smallest value in the tree? On the leaf node, right? All the way left. Where is the very largest value? All the way right. So then where is the middle value? The overall route, right? Yeah. Because there's where it's sit. Now, so those are just things to think about the structure. Okay. So yeah, is it possible to do worse? Yeah, there's our degenerate tree if we added things in that sort of like ascending behavior. So it contains key of 16. Then there you can see that was that little recurrence that I was starting to write there. That's where we get, so this is like our worst case code model. And the one on this page, this is our best case code model. There we go. Cool. So did I put it on this slide? Oh, I didn't like close this recurrence, but sorry, just so you know, then this means that this is an O of log n. We should add that to the slide. But that's how that recurrence gets evaluated. Also, if you're like, Casey, I don't really remember us talking about this. If you remember when we were at the very beginning of asymptotic analysis starting to do those recursive patterns, we talked about binary search. Remember how like the dictionary example where I'm like, oh, I'm going to check the middle value, and then if it's greater than, I eliminate all the values to the left, and then I check the middle value of that half, and then I eliminate a quarter, and then I check the middle value. It's literally doing the exact same thing, and that's also why this is called a binary search tree, and that's called the binary search algorithm. So all of those run in log n. The worst case scenario could be linear. Yeah? So different states. There's another term for this fullness that we call balance. There is a mathematical equation for how to determine if a tree is balanced. We're going to talk a ton about that because forcing a tree to stay balanced is one of the best ways to keep our runtime down because it keeps the height short. And if we keep the height short, we're going to go fewer levels down in the recursion. The taller the tree, the taller the recursive stack, the worse the runtime. Yes?
So what's the advantage of using a BST over a hash?
So what's the advantage of using a BST over a hash? So you'll probably find that they're just fit slightly better scenarios. So let's say a hash is usually really good when you have like unrelated values that all need to be held together. So for example, usernames and their passwords are almost always held in a hash. You go to a website, you type in your username, you type in your password somewhere on the back end. They're probably doing a bunch of database stuff, and that database stuff is technically a hash, and they're taking your username to go look up the password and being like, hey, did the thing they typed in, is that actually the password that I've got stored? That makes sense because like my username and password should have nothing to do with anybody else's username or password. In a binary search situation, that's when I'm maybe asking for like groups of data. Like maybe I want the bottom half of the like students in a class, and that bottom half, if we organize the keys by say student number, then that'll be the most recent students or something like that. And so you'll find that binary search trees are often used when we're talking about a set of data where the data actually relates to each other in a way that you might ask for groupings of data. We will talk a little bit more about, for example, another type of structure called tries, which kind of continues to build off of this thing, which is the underpinning of autocomplete, where technically, like if you're used to it now, right, like you're starting to type something into Google, Google's like trying to make suggestions for you, right? Those suggestions are actually stored in a tree in an organized way so that each time you type a letter, it's kind of like you make a decision, and then it shows you all these possibilities, and you type another letter and makes a decision, and then it shows you all these possibilities, and you type another letter, and it's like, it's got to be this. So you'll find that binary search trees are just used for different scenarios generally. But good question. Because you're right. You were probably like, Casey, you told us the in-practice hash runtime is constant unless we, make some bad choices about resizing or make some bad choices about hash codes. So this is going to be a best case scenario of log n time, which is obviously worse than constant, but it opens up that idea of functionality of how the data might relate to one another within each of the subtrees and so on and so forth. Cool. Let's see. I'm trying to see if any of this is not very interesting. Yeah. Okay. We will pick back up with this on Friday, where I'm going to introduce you to an entirely different category of trees that hopefully will melt your brains because they are such a pain in the arse to implement. Come prepared.